Okay, thanks. Thank you. Okay, so guidance phase. Sure. Thank you. So okay, so this course is primarily about like the title says it's about automata, infinite words, verification, and games. Okay. So today we will primarily have an overview of the whole course, and then I'm going through some slides just to give you an overview. And from the next lecture, we'll start writing on the board or maybe on the iPad. Okay. And so what is the broad idea of the course? Like, so in verification, what we do that there are these systems, okay? And in systems, there may be bugs. Huh? So you want to make sure that the systems are bug free, okay? So today the course will be more at a high level. The technical parts and all theories will start primarily from the next lecture, but just to understand what the course is all about. So what kind of bugs do exist? So for example, like in 1994, there was this Intel chip, it's the FD4. So there was a floating point computation error, okay? And that caused a cost of like the loss for the company of some 500 million USD and so on. Then there was a failure for this Mars orbiter, and the problem was again essentially like there was some units, there was this SI unit and some other units. So NASA was trying to make this orbiter, and then there was also some of the things were provided to, like outsourced to Lockheed Martin. And then there was this document which used like which said what sort of units to be used, and then things were not properly sort of like the units were not correctly they were not in I think yeah, so NASA used one unit, and whereas that's what the document was saying, and Lockheed Martin was using another unit, and that caused a crash for this Mars orbiter. And then there were these problems, which was like this Therac 25. So it was again a radiation device. And because of certain race conditions, right, like certain issues, like again, a bugs in the software, it produced 100 times more of more the recommended, like 100 times of the recommended radiation, which caused death of several people. So all these things like this can create havoc we don't want, and these are bugs in the software, right? So now, how do you ensure that these bugs don't essentially exist? So that is the idea of the course, okay? And we will see how to ensure that indeed how you can certify that the bugs don't exist in a particular software, how you can mathematically prove that the bugs don't exist. Hmm? So there are two components here. One is that we would like to correctly mathematically model the systems. Like, so for example, when you were saying that I would like to certify formally, then I should have, for example, a mathematical model of the system. And then I should also have a mathematical model of the specification, right? So we are going to see these things in more detail. And then we will sort of prove formally that yes, the system is bug free. Given the specification, given the system does not sort of like violate the constraints that are being specified by the specified by your the specification, right? So what are the requirements? The system should not violate them. So now essentially like this will be very much useful in safety critical systems. So you can get to see all these softwares, for example, in cars, production plants, warehouses, airlines, and some of the things where this formal verification is widely used. So, for example, in airlines, so if you go to any of the modern airports, there are these systems like it's called a RIMCAS, runaway incursion monitoring and collision avoidance. So essentially, there may be flights which are landing and then taxiing and they are taking off. So there are runways. So there is a runway, there is a taxiway. So how do you ensure that all these flights they are not coming in the way of each other? Right? So there are these different systems, and not everything is controlled by the ATC. So these are concurrent systems. They are kind of simultaneously they are running, and you want to ensure that that some kind of crash doesn't happen and the planes don't come in the way of one another. And there are some other things also, like there are these systems called runway status lights, and a lot of, like, for example, a verification process that goes into the development of these technologies. So it's not only, so we are primarily going to, I mean, in this course, so this is just, as I said, the overview. Primarily, we are going to look at the theory part of, like, the theory behind all these softwares. But what I'm trying to say that they also have a lot of applications, which possibly after today, we are not going to look at much of that. But we should be aware of the fact that the things that we are going to learn in this course will have abundant, I mean, abundance of applications. So then there is another thing which is called this ACAS, which is Airborne Collision Avoidance System. So this is for the flights which are already there airborne. So the flights are moving and you want to ensure that two flights don't come very close to each other. So there are these kind of software also. Though the ATC also keeps monitoring these kind of things that the two flights are not close enough, but at the same time, there are these other things which are also, which usually run independently. Now, when we are having these specifications, it's also important that the systems are modeled correctly. So what we are saying that usually we would have, for example, like a system. Okay, so I will say, suppose there is a system and then there is a specification file. So it means that whether the model, it satisfies the specification correctly, right? So I have an M and here I have a specification file. I want to ensure that this model satisfies the specification correctly or not. It's also important that the model is, I mean, the system is modeled correctly. So this is important, and the specification we assume, let's say it's given correctly, in which case we want to ensure that the model is also correct, right? So I mean, what a model essentially means, that also we'll get to see in the course of the lectures. Okay, and now there are specific kind of systems that we'll be looking at in this lecture. So, and in this course, so these are called reactive systems. These are called reactive systems. So reactive systems are systems which are not necessarily terminating. So they keep on interacting with the environment. So usually the environment would send a signal, and the system would react to the environment. So that's why they are called reactive. Okay. So there is a, like, you can think of, like, there are these discrete time steps. I mean, they can be not necessarily discrete. I mean, it can be continuous also. But for the time being, let's consider that these are discrete time steps, and at which the system is getting inputs from the environment and it's reacting to the environment. Okay. And the idea is that, like, so it continuously interacts with the environment. And there are several things like this, several reactive systems we get to see in our day-to-day life, and there are several such systems. So what it results into is a non-terminating interaction. So there is this, as I was saying, there is this environment, there is this system, and the environment sends an input I, and the system reacts to the input. Okay, and it continues forever. So you have like I0, 0, then the state of the environment evolves from E0 to E1, and the state of the system evolves from S0 to S1, and so on. It's an infinite execution. And what we want to ensure that this infinite execution, it does not violate the specification that is said. So if you talk about some safety specification, that something needs to be safe, or if you say that something needs to eventually happen, right? So this kind of things should hold true, right? So this execution should not violate such specifications. Right. So there can be several examples of reactive systems. For example, you can have like a chipset in an operating system. Maybe the system is running forever. Then several of these, embedded devices, your wireless device and other things. And then there is a satellite, artificial satellite. So these are all examples of reactive systems. So reactive systems, they appear in abundance around us. So it's not something which is we don't find, but it's something that we get to see all the time. Now, as I was saying, what is formal verification about? So formal verification is about that we are given such system specification, there will be a design process. Then usually we would make a prototype, right? A prototype of the system, right? So a prototype of the system. So sometimes what happens is like the whole system we may not be able to verify directly. So sometimes we would like to abstract and get a formal model of the system. Okay. So often we will see it's in the form of an automaton, for example, or maybe some other kinds of machines, right? And so this is what I'm calling the system model. And then we are given also certain properties here. And here comes the verification process, which takes the system model and the properties and the checks whether the system model it satisfies the properties and some bugs may be found, okay, or certain bugs I mean no bugs are found, in which case we would say that the system is correct, and we will actually formally or mathematically will certify that the system is correct, and uh, we are fine. Okay. And it can also happen that if there is a bug which is found, then we might say that we would also like to find out why there is a bug. So there can be a counter example, like which says that, well, yeah, if the system executes in this particular way, then this execution is going to violate the specification. Okay. This particular execution is going to violate your specification, in which case, if you transfer this knowledge to the developer might from that knowledge try to fix or make some changes to the code, and in which case maybe the next time the system starts satisfying the the specification. Okay. And this is just to give you an idea of like how large this this verification industry is about. So uh so this is a talk I heard from someone called Ziad Khanna, who is a at least like 3 years ago, he was a senior vice president of Intel, and he was there in this conference called Flock, and he was saying that by 2030, this electronic design automation industry, EDA industry, that's going to be like $1 trillion chip design. So unfortunately, like we in India don't have such, like chip manufacturing companies. I mean, there are maybe very few. It's mostly in Taiwan and other places. And a lot of money, whenever suppose there are these chip designing companies, a lot of money is involved in this fabrication, like the actually chip fabrication, and a lot of money is involved like in fixing the defects. Like so, if there is a fabrication that happens and you find a defect afterwards, then again you have to kind of make the changes, and it goes for the fabrication once more and things like that. So I know Rahul was at some point of time, he used to work in, like in a chip designing company. So if you get to talk to him sometime, I think he can give you more details about the entire cycle that this chip designing goes through. I mean, so there'll be a PHI team who will be working on like the actual communication, like for example, how your signal will be modulated, coding and all that, and there'll be several layers. And once all those things are sort of, checked in the software, then they ship it to this to the fab, and then the fab would do things, and the chip would come back, and then there'll be the testing and the verification, and the verification like these gates and all. They will check, and if there is a bug at that level, then fixing that would usually cost a lot of money. And now, if you look at all these companies, for example, Cadence, Synopsys, yeah, and even for example Microsoft, they all have their own verification tools which they would use to ensure that there are, I mean, this whatever they are producing, they are bug free. Okay, so this is all, and yeah, so this is something that I found just to sort of motivate about like why formal methods is necessary, what's the importance of formal method. So this is something that I found in a report from, I mean, it's from one of the textbooks, which we will look at once in a while. So it talks about this, that there was a report by this Federal Aviation Authority and NASA, which says that formal methods should be part of education of every computer scientist and software engineer, just as the appropriate branch of applied mathematics is a necessary part of the education of all other engineers. So just something I felt like something to uh, motivate and understand the importance of formal methods and formal verification. Okay, so again, coming back to what formal verification is about. So we are given a formal model of the system. So what is a formal model of the system? So for example, we have an actual system, we have the software, but it sometimes may be very difficult to actually sort of like, to verify the software directly. So we would like to have an abstract model of the system, which I will call it as a formal model. It describes the system behavior, and then we also have the formal specification. And how is the formal specification given? It's usually given in the form of a logic formula, right? Usually it will be given in the form of a logic formula, because we want to formalize things. It cannot be in some, like in a language which we speak on a daily basis. So something, for example, if we have a logical formula, that will kind of be very specific, it will be unambiguous and things like that. So the specification usually is provided in the form of a logic. And we'll see in more detail that it can also be again in the form of some automaton also, like anything which describes a language unambiguously. A specification can be thought of as a language as well, right? A specification can be thought of as a language in the sense like a specification would describe a set of executions of the system that, like, let's say a set of executions that the system should not violate. So you can consider the specification also as a language. Is it clear? Like the specification can also be thought of as a language. Okay. Sorry. Okay. So and what is our objective? So the specification says what the system should do and what it should not do. And the objective is to show that the system satisfies the specification by generating a formal mathematical proof, right? So, and we will see that logic and automata form the backbone of such formal mathematical proofs. That's the thing that we'll start seeing from the next lecture. Okay, and so this is also something I found very interestingly. So it says that as the lines between software and hardware blur, so this was about just a non-technical article about, like, I think at some point of time there was so Toyota had some bugs like in its ABS in one of its cars, and they had to recall all the cars, like, and so it was again a verification problem. And then this article somebody wrote, and it says that, like, so where do the bugs these days lie? I mean, it's there in operating systems, applications, cell phones, pacemakers, PowerPoints, medical equipments, power plants, and also in our cars and things like that. So these bugs are also ubiquitous. So as software is ubiquitous, these bugs are also there. Okay, so now a specific kind of algorithmic process to ensure that, like, I mean, which is there in verification, it's called model checking. So what is model checking? It's an algorithmic procedure to ensure that our systems satisfy the property. So what does the model checker does, as I was saying? So the idea is that we have the system model, we have a property specification, and the model checker. It's kind of it's just an algorithm. So the algorithm would take the system and the property specification. If the system, for example, if the system, let's say S, it satisfies the property phi, then it will say true. Otherwise, this algorithm will say false, and it will generate a counter example. So what is a counter example? A counter example is primarily an execution of the system which it shows that is violating the specification, right? A counter example is an execution of the system that is shown to violate the specification. Okay, so now when we have such an environment, and as I was saying, that we have the environment and we have a system, usually these are like reactive systems. So what happens is like the environment and the system, they are executing together. The system is getting inputs from the environment and it's giving some output. So we can think of this as some kind of a language, okay, which is a product of the environment of and the system, right? It's like the environment is acting and the system is also responding. And we can consider this to be like the environment can give you different inputs, right? The inputs can come, say, I1, I2 like this, and the system is producing outputs O1, O2 like this. But maybe some other time, the environment may give you something like I1 prime, I2 prime, the system is producing O1 prime, O2 prime like this, right? So this is an infinite word, right? This is an infinite word which is getting generated. And here, this is another infinite word which is getting generated. So the set of all these different possible infinite words, we can consider this as a language of infinite words, right? And such languages, we will call them omega language, or these words, we will call them omega words. Omega words. Okay? Is it clear? And then as I was saying that we have this specification, it's a phi, and this specification is called, like I call this as particular kind of a logic with which I'm going to describe this specification. It's called LTL, linear temporal logic, which we'll see. Okay, linear temporal logic. So often the specification is given in terms of such logical specifications. So the logic will describe the behavior which is expected out of the system when the system is interacting with the environment. Okay, and this logic, which we will often use, and we will also study this in more detail, it's called the logic LTL, linear temporal logic, and it's widely used again. So what we'll look at is LTL verification. I mean, like when we are going to study about the verification of systems, the specifications like against LTL specifications. So these things we will study in detail. And then often we'll also look at, for example, guarantees. Like when you talk about the specifications, you want some kind of guarantees out of the system, right? That the system should satisfy such properties. So, and the models of the system, what are the different possibilities? I mean, the different kinds of systems we can think of. Like, for example, the system may have probabilistic behavior. You can say that maybe this light will fail with some probability after a certain amount of time, right? So, and one formal model, as I was talking about this formal model. So one example of a formal model is an automaton. Another example of a formal model with which you would like to describe probabilistic behavior, that, for example, is a Markov chain. Okay, so the Markov chains, I mean, for example, may be used to model communication over a lossy channel. So when I say lossy channel, it means that there is some probability that the message may get disappeared. I mean, the message may disappear with certain probability. The message may not reach your target, the intended target, with certain probabilities. There can also be queuing networks, and then there are these predator prey, etc. I mean, there can be several such models where there are probabilities, and this kind of things you would like to model with this Markov chain. And yeah, and they are widely applicable in various, like in biology, for example, in epidemiology and study of chemistry and things like this. And we'll particularly also see, for example, this is something called a Markov decision process. What is a Markov decision process? It's a generalization of Markov chain. Okay, so in Markov chain, so if you know, you have, what do you have in a Markov chain? So in a Markov chain, you have some state, and then you have a probability distribution over successor states. It's a probability distribution. So for example, you can say that I have points 3, 0.2, 0.5 like this. So what it means is that from the state S, I may go to state S1 with probability 0.3, to state S2 with probability 0.2, and to state S3 with probability 0.5, and so on. Whereas in the case of an MDP, Markov decision process, we have also a non-determinism. We also have a non-determinism. So what is the non-determinism about? Like, so you can have multiple possible probability distributions. You can have multiple possible probability distributions. So for example, I may have a green distribution, another green distribution, sorry, a blue distribution from here. And the non-determinism is about which one to choose. So whether to choose this one or whether to choose this one. Or I can have a distribution over the distributions, right? So if I call them this violet and the blue one, these distributions as actions, I can call uh, for example, to resolve this non-determinism, I can have a distribution over this action. So which means that I can choose the violet distribution, let's say with probability 0.3 and the blue distribution with probability 0.7, right? So that's how I'm resolving the non-determinism. So where are Markov decision processes used? So it's not exactly so. The Markov decision process, strictly speaking, is not a system. It's not a system. The Markov chain is a system. But then you can talk about, like, in order to satisfy the specification, what sort of distributions I should choose over the actions in order to satisfy the specifications, right? So for example, like if I come to this particular state S, then what should I do? Like, should I choose the violet distribution entirely, or should I do a mix of the violet and the blue distributions in order to satisfy my specifications, right? So this is what is the MDP about, and I will tell a bit more about this. It will be a bit more clearer when we talk about something called reactive synthesis in a while. Okay, so the reactive is again, it's the reactive system, but the synthesis is about synthesizing a system. So here the system is not provided, but I'm saying that can I generate a system such that no matter how the environment behaves, I should always be able to satisfy my specification. Okay, so for example, here I am given the Markov decision process, which is not really a system. Once I choose my policies, so when I say policy, it means that when I come to a particular state, how am I going to choose from the available things that I can do, such that as a result of that, whatever system I get, so I have many choices, right? That's the non-determinism about. I have different choices. So what should I choose? How should I resolve my non-determinism so that the resultant system satisfies the property? Okay. And these things are also used in probabilistic programs. So what are probabilistic programs? I mean, these are usually programs which have access to some samplers that can generate random numbers from predefined distributions, right? So for example, when you use some kind of a seed and rand of some seed and these kind of things in your program, so these are usually examples of probability programs. And I mean, all our randomized algorithms, network protocols, these are examples of probabilistic programs. And some logical specifications that we'll see. These are like LTL, as I said, and then one thing is like PCTL, which is a probabilistic computational tree logic, right? So now if you have, for example, a system which is a probabilistic system, right? You may also have properties which should also have probabilities in it, right? So there is a system which displays certain probabilistic behavior, and you may also want to say that with zero 0.8 probability, this light should not fail in the next 2 years or something like that, right? So how would you specify such behavior? How do you specify such property specification? So that specification should also consider probability in it, right? So certain logical constructs we would like to use that allows one to use probability. So one such logic which allows probability to be used, it's called PCTL. So I don't know whether we'll be able to see all of them, but we'll see maybe some of them. And there are different kinds of properties. Why do we talk about these different kinds of properties, like segregation of different kinds of properties? The reason being, you will see that some properties it might be easier to verify or check. Some properties it may be more difficult to verify and check. So it's in terms of when we study the complexity results associated with this algorithm. So we are talking about this model checking, right? Which is essentially an algorithm. Now, when we study these algorithms, so what we will be looking at, we will be looking at the complexity associated with these model checking algorithms. So this is something we are going to study. And for what kind of properties, for what kind of logic, so what sort of complexities are associated with this verification process, right? Something may be easy, something may be more difficult, something may be even undecidable. Certain kinds of properties to for example in synthesis, maybe it's completely undecidable. I mean, you may not, given a particular kind of specification, there may not exist a procedure to figure out whether a general policy exists to satisfy the specification, right? I may not even have an algorithm to decide whether a policy exists to satisfy such specification. So these problems may be undecidable, right? And certain policies, I mean, certain kind of things may have higher complexity, certain kinds of things may be lower complexity. So these are the kinds of things which will be studying in more detail. Yeah. So what is a safety specification? So safety specification is primarily it talks about that something bad should not happen, right? So this is about the safety specification. So when I say something bad should not happen, then usually it is the case that you have, like, let's say you have an a system, then the system will have like multiple states, and then you may say that, well, these are my set of bad states, right? So then what you would like to ensure that your system never goes into that bad region. It's always outside the bad region, which is considered to be safe, right? So these are the safety specification. Then liveness is about something good should eventually happen. Like, I mean, so for example, if I say that this is a good state and maybe you are starting from here, then eventually you should see the good behavior, you should see the good state. So this is about the liveness properties. So for example, a coffee machine should eventually produce coffee. It should give you coffee, right? And then fairness is kind of a property which is like requests which are made infinitely often should be satisfied infinitely often. Okay, so this is about fairness. And there can be quantitative properties also. Like, for example, when I say if I have a Markov chain, for example, I may want to visit this particular state, but I may not say that I will be able to visit it across all the behaviors, across all the executions of the system. I may just want to maybe able to say that you will be able to satisfy this eventuality property or this liveness property with certain probability, right? So this is where these are like certain kinds of uh, yeah, like some quantitative property where there's a probability of satisfaction. And then another kind of uh, another kind of property which involves probability is expectation. So you want to say that, well, I don't want a probabilistic guarantee, but I want some kind of an expected value to be higher than, like, so for example, like, let's say you have made an investment, right? And you want to say that, well, there may be some losses, there will be some gains that you get, there may be some profits, and then, but you want to make sure that in an expectation, every year I would like to get this much of return. So the expected return should be this much, right? So how would you verify these things? Or if you are given an MDP where there are many possibilities, right? So you can, for example, if you have, let's say you are investing, then how you should invest across different portfolios so that the expected return should be at least this much. So it's like a policy that you have to choose, and the MDPs are used there. So you have a formal model where you say that, okay, these are all my different non-deterministic choices. These are my choices. And how should I, what should be my policy? What should be my strategy so that my expected return is something like this? And we'll see different kinds of strategies. Like, so for example, certain strategies are very easy. Like, it's to implement that strategy, it's like you don't need much complexities in it, in the sense that you don't need to remember something. I mean, it's just what we are often called Markovian policies, that you reach a state and the policy just depends on that particular state. Sometimes you will see that, okay, I need more complex policies. I may have to remember something about the history, that, okay, maybe 3 years ago when I did use this policy, I did not get much returns. I have to remember that history. So this time I have to do something new, right? So these are like histories which I need to kind of keep in mind. And there can be also things like energy consumption, response time. So these are all examples of quantitative properties. Okay, so and again, like not all logics are equally expressive. So some logics are less expressive. So if you are talking about specifications, then we have to also find the right kind of formula, the right kind of formula, logic formulas, such that the logic is expressive enough to talk about that property. But then it should not also be very complex, in the sense that if it expresses too many things, if it expresses like, yeah, I mean, too many things, then what can happen that algorithmically to check this particular specification, whether the system satisfies that specification, the complexity may be too high, right? Or it may even become undecidable. We don't want that. Ideally, we want something which should be expressive enough, but at the same time, the complexity should be low, right? It should be within acceptable complexity. So tomorrow, if you come to me and tell me that, okay, I have this system, I have this car, I have an ABS in it, and you have to verify, let's say within 4 seconds, if I press my brake this much, within 100 meters it should stop, right? And if I have a logic, and if I have a generic logic, generic algorithm which takes your specification and this logical formula and tries to verify whether this holds, and if it takes maybe like a year, then you will not be satisfied with me, right? So the complexity should be low also for this verification process. Right. And I mean, when people actually do these things in the industry in practice, then the kind of things that one checks, or the challenges one would face, is the model correct, right? One thing is that is the model correct. Like, so when I'm given, suppose you are coming with your car, right? And then I have to get an abstract model out of it, right? Which can be an automaton or a Markov chain or an MDP, all these things that we were talking about. I have to make sure that I correctly capture the behavior of the system. And then I also have to sort of formally see that if the specification is correct and complete, like whatever you were looking for, that thing has been taken care of. Right. So now we are going to talk about here formal verification and not testing. So what is the difference between testing and formal verification? So is there anyone who has worked in the industry here like before? No. Okay. So I mean, so if you go to the industry, like, so there'll be engineers who are developers, then there are testing engineers and things like that. So what do the test engineers do? They will have a set of test cases, right? So uh, whenever there's a development of the software, like you are developing a tool or whatever, and then whenever there are some changes to that tool, let's say, so you will have a set of tests and you will run them with your new version of the tool to make sure that your development did not introduce any new bugs. Okay, so this is like testing. So what does testing show? Like if there is a bug, then it will point out that bug, like, oh, I had say 1,000 test cases, and now I made some changes, and maybe 5 of the test cases now start failing. So it will say that, okay, the new introduction of the new feature was good maybe, but there are certain things which were working earlier, they have started breaking. So there are some bugs. So testing can tell you the presence of bugs, but not their absence. Why not their absence? Because it's not complete, in the sense like you cannot usually test all the features. You cannot test exhaustively in most of the cases. You can only say you have the test cases and you run those test cases, and then you say that, okay, like there can be a bug, there is a bug, but you cannot certify that there is the absence of bugs. So formal verification will talk about the absence of bugs. So when you certify mathematically, then it will actually say that indeed the code or your system does not have any bug with respect to that specific property. So this system is not going to violate this specific property. So that's the thing. Okay. And testing, as I said, it's not necessarily always exhaustive. So so again, what are the challenges? So the challenges are modeling the system, modeling the specification. Then one of the things that people would often face is about the size of the state space. Like, so because any realistic software that you take, it may have millions of states, like, and then you want your algorithm to be really efficient. And so often this is one thing that things in real life, people, why do they testing? Like if you go to, for example, any of the companies in the industry, people are not doing formal verification. Only the very specific people, like for example, those who are doing dealing with hardware, they have their formal verification tools. Whereas in the case of software verification, we primarily, people in the industry, they do testing, because the formal verification tools, even today, they are not at the level such that they can scale in proportion to the size of the softwares that we have. So that's a very big challenge. Okay. So there are different kinds of techniques, for example, that people use. For example, compositional verification. So you use small modules, and then they are relatively easier to verify. And then if you can give guarantees on the individual components, then you can give guarantees to the whole system. And then there are things called abstraction. So abstraction is like, as I was saying, that you have the actual system. Can I abstract it into some form of a formal model? Like I can model it as an automaton, I can model it as a Markov chain, as an MDP and things like that. But then the problem with the abstraction is that I might lose some details. And when I'm losing some of the details, whether is it everything correct, like whether every specification that I want to check, am I losing something? So these are the kinds of things that may, I mean, these kind of things can happen, like when you are talking about abstractions. And then there are different kinds of tools that people use. So one is like one set of tools, they are called theorem prover. So there are these proof assistants. So what happens is, like, you are given this specification. So this is again, I mean, if someone wants to study theorem prover, proof assistants, it can be a separate course altogether, like programs and proofs and this kind of thing. So there the idea is that you are given a logic set of axioms and then set of inference rules and things like that. And then sometimes it would also require some human intervention, because the proofs cannot necessarily always be automated, and it will require some human intervention. So if there are different kinds of possibilities about what are the proof rules that one can use, so you can kind of guide the theorem prover. Okay. And nowadays, even people have been using a lot of these LLMs or AI things, like, so that the human in the loop can be sort of, that can also be automated to some extent, right? So there are certain things called lean and all. If you talk to Piyush, for example, he can tell you a bit about those sort of things, or maybe Jatin also. Right. So, and what are the standard model checking tools, at least, which are there in academia? So we might see a couple of them later. So these are, like, there are these tools called Spin and Mu Assembly. So these do like for standard model checking, which are like LTL, CTL, where we are not talking about probabilities in particular. So, for example, as I was saying, that you have this system M, and then there is this phi. This may be given in LTL, like linear temporal logic. And it will either say correct, or like it satisfies, or it will say false and with a counter example. If it says it does not, then it will generate a counter example, which you can actually sort of carefully try to understand and maybe make some changes in the system, right? After looking at the counter example. And there are probabilistic model checkers also, for example. So these are some probabilistic model checkers, Prism, Storm. And there is also something called a timed automata. So what is a timed automata? So there may be different systems and properties where time is an important thing. Like if you are talking about, let's say, a cyber physical system, huh? Or something where, like, you want to say that this thing should hold within this much amount of time. So what is the abstract model? What is a model to capture those properties, right? So what is a good formal model to capture those properties? So their timed automata comes into picture. So, and there are tools also for timed automata, so which is called UPA. So there are different kinds of such tools. And so all these are fairly automated. There are this counter example generation, and then UPAL, for example, is also used in industry. And then again, like, we'll see that these are like, so when you provide a guarantee, it comes with this mathematical this guarantees and all. So where are formal methods used? Some examples here. So Microsoft uses for its device drivers very largely. So I'm just saying that, like from the next lecture, we are going to look at primarily the formal models. We will start with the theory, but then, as I said, like it has also a large amount of applications outside academia, in the industry also, and um, yeah, and so there was this particular protocol, Needham-Schroeder protocol, which is about it uses a public key cryptography for sending messages from one node to another, and there were bugs in that protocol, right? So the algorithm which implements that protocol was buggy, and then there were formal method tools which or algorithms which could find out such bugs. And there are people who are very specialized to work on security, cryptographic security protocols. They, for example, they specialize in verification of cryptographic security protocols and things like that. So um, yeah, and so, as I was saying, like for example, theorem proving and verification of certain kinds of protocols, reactive synthesis. So these are all different. So it's just a very first course on verification, but these are all different areas in which are related to formal methods and verification. So somebody who works on cryptographic protocols may not be that, may not be an expert in reactive synthesis, for example, or someone who is working on theorem proving may not know well, for example, the complexity of the logics, for example, and this kind of thing. Someone who is working on probabilistic verification, may not necessarily be an expert on timed verification, for example. So these are different kinds of sub areas under verification and synthesis, so to say. Okay, so just some history which are related to this area. So in 1976, Michael Rabin and Dana Scott. So, for example, if you have heard of this term called Scott-Rabin automaton, right? Scott-Rabin automaton. So, this is nothing but our simple non-deterministic automaton, NFA, right? So, the non-determinism is used in a it's again, it's used everywhere. Like you have this notion of non-determinism, and then you can talk about Turing machines with non-determinism with different resources and things like that. You can talk about NP machine, NP space machine, NEXP machine, and non-deterministic automaton. But the non-determinism is very it's a very basic sort of an idea. And then you kind of add resources and to have different complexity classes and things like that. So then there was in 1996, Amir Nueli, who came up with this idea of linear temporal logic. So his work on temporal logics, it brought this Turing Award, and then he kind of started this whole area of model checking, which was later made popular by these people, Ed Clark and Emerson and Joseph Sipakis. And then this was a pioneering work around the 2000 when Pierre Wilfer and Moshe Verdi, what they did was so if you have this LTL, linear temporal logic, then how can you, for example, what is the complexity? So it's a for LTL specification, like so he showed a logic automata connection. Like you can construct something called a bookie automaton, which we'll start with either toward the end of today or from the next lecture. That how you can translate from LTL to bookie automaton in order to do the verification, to facilitate verification. Okay, and we'll see essentially often that when we are talking about these verification problems, they will often be reduced to emptiness of automaton, right? So how do we check, for example, that a system satisfies a particular specification? This problem will be reduced to automaton emptiness problem, right? So these are the kinds of things we'll study. So yeah, these are very some of the very important works. And so far I was talking about the verification problem, right? So I don't know if some of you were there In last week, this Bharat's lecture, Bharat Artsul, so he was giving an invited lecture in that STCS symposium. This was the last invited lecture. So he was talking about this synthesis. So this is like Alonzo Charge. He proposed this problem in 1957. So it's also called the charge synthesis problem. So exactly this thing, like I was talking about the input and the output, right? Like, so the verification is about like there is a system and then there is this environment. So the environment is coming up with such inputs, let's say I1, I2, I3, I4, etc. And the specification is actually, it's a language. As I mentioned, it's a language over these omega words, the input cross output omega. And here, so I have the inputs I1, I2, I3, I4, and the outputs are like O1, O2, O3, O4. So what I want to ensure that the resulting infinite input output sequence like this, which are being created like this. So this sequence, this is an infinite sequence. It must satisfy for all such input sequences, right? So for all these input sequences, the output that is being generated, okay? So these are coming from the environment and the system is producing these outputs, right? So this sequence, right, which is an omega word, should be in the specification language fine, right? So that is the problem. Now the question is that if we are given such a specification, then can we come up with a circuit? A circuit is nothing but an algorithm or a program, right, which will satisfy this specification. So the question is that uh, can such a circuit realize phi? So this is the question one would ask. Can a circuit, you design a circuit C which realizes phi? It's already written here. Design a circuit C which realizes phi. So which means that essentially given this input stream, can I produce the output such that the language satisfies this specification phi? Okay, so here, so this is the synthesis question. I'm given this environment, and then I have to synthesize such a system such that it satisfies the phi, which is maybe an LTL specification. So here, earlier, if you remember that in the case of verification, I was given this, and then I asked this question, like if this satisfies phi, right? And the way one would do this, I mean, the algorithms would work. From phi, I would construct an automaton A phi such that the language which corresponds to this phi is the same as the language of the automaton A phi. Okay, so that's why I say that the language which is produced as uh, because of the interaction of the environment and the system, whether this is included in the language of the corresponding automaton. So if this is the case, then it means that you are not violating the specification. Okay. So is it clear? Like, right? So I'm given the specification. What I'm saying is that I will construct an automaton. So how we construct that we will see. So these are kind of complex procedures, complex steps. There are algorithms which given this logical formula phi, it will construct the automaton such that the language of the automaton and the set of words which satisfy phi, they are exactly the same. Okay. And how we do that, these translations we'll see over the time. So that is the idea. And this, the synthesis can be considered to be as a, one can view this as a two-player game. So what is the idea of the two-player game? So what are the two players? So there is this environment and the system, right? So these are the two players. So I can also consider the environment as a, I will sometimes call it as a max player or a min player or player 0, player 1, but essentially these are the two players. And what is the objective of the environment? The objective of the environment is kind of to defeat the system player in the sense that produce some kind of input, right, to which the system respond, cannot respond properly, which means that the system cannot respond in a way such that the specification is not satisfied. So, right, so suppose I'm playing with you, you are the system, I'm the environment. I'll give you some input such that you don't have a way to produce the output which will satisfy the specification Like the generated word, the generated infinite word will not be in the language of the specification file, right? So if you recall from your theory of computation course, a language which is given by a phi is nothing but a problem, or it's the language of an automaton and the language of a logical formula. So they are all kind of, I mean, you can consider the language as a problem in some sense, right? So yeah. So this is the objective of the system. The objective of the system is the specification phi. The objective of the environment is the negation of phi. Okay. So it's a two-player. We call it a two-player zero-sum game. Why it's zero-sum? Because if, for example, the system wins, then the environment loses, and vice versa. Right. So it's a zero-sum game. Okay. So now we say that the system player wins if the run belongs to the language of the specification, otherwise the environment wins. Okay, so you are playing, and the system, given the input to the input of the environment, the system is trying to find an output, right? The system may need a strategy, a policy to find the output such that the resulting string is in the language of the specification. So yes, the system player wins if the run is in the language of the specification, otherwise the environment player wins. So we want a strategy of the system player. We want a strategy of the system player that wins against any strategy of the, irrespective of how the environment plays, I should be able to win against the environment. So that's like my strategy, okay, against the strategy of the environment. And if I say that I have a winning strategy, right? So now if I have a winning strategy, when I apply my winning strategy, then I will have a system which is like executing. So a winning strategy essentially corresponds to a realizable phi, that I can actually have a system which can be correctly constructed. Right? So that is the idea. Okay. So this is where we will talk about this. So one part of the course title is infinite games. So we'll talk a little bit about these infinite games also. So you see where these infinite games come. I mean, these games come from, right? So you have the specification, you have the environment, and then I want to synthesize a policy such that the resultant system, it will satisfy the specific requirement. Hmm? So, so initially here the system is not given. So I'm synthesizing the strategy. So that's why it's called the reactive synthesis, right? I'm synthesizing the strategy. How? By getting a policy. So when I apply the policy, then I get a system, right? So if I apply a policy on an MDP, Markov decision process, I get a Markov chain, which is the system, right? The MDP has non-determinism. So I have to come up with a strategy. I apply the policy or the strategy, and then I get a system. And there can be different kinds of strategies like our policies. So some policies are simple, as I said. Some policies may need a lot of history. Some policies even may need infinite amount of history. Some policies may not require any kind of randomization over the probabilities or the actions, or the probability distributions. Some kind of policies may require some, like randomization or mixing of the distributions. So there are all these different kinds of policies can be there. And then this chart synthesis problem can be seen as a game. Like, I mean, as I was saying, that it's a game in what way? That my input alphabet, is of this form. My I was ABC. Let's say my O is 1, 2, 3. So if I, for example, I can say that the whatever be the input, my specification can be like, I would like to see 1, 1, 2, 2, 3, 3 omega, something like this. This pattern has to be repeated, right? So you need some memory. Why you need some memory? Because initially, suppose you start from here, then once the input comes, you would like to stay here. Then again, the input comes, you would like to stay here. After that, so you know that I have already been here twice. So now I need to output 2. So I'll go there, and then I will stay here twice. And then right? So this requires some amount of memory. So this policy requires some amount of memory here. So, and then I'll give an example of a very simple type of a game, like which I was talking about, like, for example, this eventually something needs to be satisfied, right? Like it's called a liveness property. Something good needs to happen. So let's say you would like to say that L3 is a good state. So I would like to visit L3. Maybe when you go to L3, you recharge your battery, like something like that. So you'd like to visit L3. And so these two-player reachability games. So this is controller. It's a model for controller synthesis, a formal model for controller synthesis. Why do I say controller? Because it's like the controller. A controller usually has certain policies, right? So I'm trying to find a policy here. So the way it would we can abstract it and model it using is like it's a game on a graph, right? So they're often called graph games, right? So these are games on a graph. And again, we are talking about two-player zero-sum games, where what are the two players? So the two players are there is this environment player, which is the circle player. Sometimes I'll call it even like player zero or the min player. And I have this is the system player. The circle is the system player. And the square here is the environment player. Okay, environment player. Right? And I will also call it maybe sometimes mean. This is maybe a max player, but essentially they're the same. It's a zero-sum game. And the way I can think of this is like there is a token which is initially placed in the initial state. So there is a token which is placed here. And in every round, the player who owns this particular vertex. So here L1 is owned by the system player. So the system player would move it to one state. So here there are like two possibilities. The objective here is that can I reach, let's say L3? Can I reach L3? This is my objective. Can I, as a system player, reach L3 against you as the environment? Whatever way you play, whatever way you as an environment play, I should be able to reach L3. Now, if I ask you the question, like, so every time, whenever I am in the system state, like if I'm in a vertex which is owned by me, I'll move it to one of my possible choices, right? So I can either go here or I can go here, right? So since if I go here, there is no way I can hope that I'll be able to reach L3. So what I would do, I would ideally, being a rational agent, I would like to go here, right? And then from L4, what can happen? Like, so suppose again, I just have one possibility. So I go here, right? But now the environment can always send me back, right? So here I don't have a policy to actually reach L3. So this objective, which is like reach L3 irrespective of how the environment behaves, doesn't work for this specific game. Okay. Now, what we will study? We will study about the complexities. How do we find a strategy? Whether a strategy exists, whether a policy exists. Finding such a policy, what is the complexity of that? This kind of things we will study. Okay. Is it clear? Right. So, yeah. So I think I said a strategy for a player from a vertex V that he or she owns is an edge or an action that is chosen from V given a finite run ending in V. So a strategy is essentially, you can say that's a strategy for player circle or player system is like a sigma. It's a function given a history, right? Given a finite history, suppose you are reaching here in a circle vertex to this, to another vertex. So this is the strategy, correct? And this is a deterministic strategy here, just to keep things simple. Like I'm not doing any kind of randomization. Here I'm just reaching, I don't need a more complex, like a randomized strategy. Right? I don't need to mix among my outgoing edges. Okay. So this is the definition of a strategy. So I've seen some finite history and I am in a vertex. I am in this vertex. So by V circle, I mean the set of vertices. So V is partitioned into like V equal to V circle. It's partitioned into these two sets. And when I'm reaching a vertex which is owned by a system player, from that, which outgoing edge I should check. Clear? Is the definition okay? Right? So Now, this is just a statement which is like it's a theorem, I mean, say, quite a well-known theorem in this work, which is related to reactive synthesis, that it's decidable. So, given a specification in S1, S or LTL, okay, so it is decidable that if such a specification is given in this language, right? So the specification is given in S1S. So what is S1S? We'll see this. It's a monadic second order logic of one successor, right? So do you understand like what is monadic second order logic? Okay, so I think we'll see that. So monadic second order logic of one successor. So so this is essentially the MSO which we saw when we say one successor. It's on words, right? So if you have like, so you can think of like, for example, there is a word, let's say A1, A2, A3, A4, like this, huh? So it can also be a finite word or an infinite word. So every letter has just one successor, every letter. So you can think of this as there are positions like position 1, position 2, position 3, position 4. So every position has just one successor, right? And monadic second order logic is a logic which extends strictly first order logic. So, some of you are familiar with first order logic, like have you seen? But if not, we'll see that. Okay, so a monadic second order logic strictly extends first order logic, and then it's like if the specification is given in this kind of logic, and or it's given in linear temporal logic, such things, then the charge synthesis problem, like can I come up with a circuit? Is there a circuit which is realizable? This problem is decidable. Okay, and all it requires is a finite state program. So when I say finite state program, it essentially means that the policy can be implemented with finite amount of memory, right? You don't need, sometimes there can be policies which might even require infinite amount of memory. So you essentially need to remember the entire history, like, okay, so here it says that you only need a finite amount of memory when the specification is given in this particular, these logics, linear temporal logic or monadic second order theory of one successor. Okay, and you can have an algorithm to construct the circuit. You have an algorithm to construct the circuit. So this is the Bushi Landweber theorem. And I was talking about this MDP, the games on MDP. So an MDP, I'm just showing nothing much here, just an example how an MDP typically looks like. So you have like all these colors are nothing but some distributions, right? So I was talking about this distribution. So a green distribution here, a brown distribution. Here there is a yeah, brown, green, and a blue distribution. So there may be certain specific objectives. I did not mention any specific objectives. Depending on the specific objective, you may see, like if you just want to talk about reachability, right, with certain probability and all, eventually you would like to reach, then a very simple like a Markov policy should suffice. Like you come here, you would always choose one of the outgoing edges. Okay. And if you, on the other hand, say, for example, I would like to reach there in certain number of steps, then you might see that, okay, the steps, you might need to remember that how many steps are already over and things like that. Some amount of history may be needed. And sometimes you may see that for certain kinds of objectives, I mean, one may even need infinite memory, like, I mean, right? And maybe may require randomization. So sometimes you may, well, if I come here every odd number of times I reach here, I may have to do a mixing of the brown and the green. Every even number of steps I reach here, I may have to do a mixing of the brown and the blue, something like that, right? So this kind of, so these are different kinds of policies one might need to think of depending on the objective, the specific objective. Not all objectives are of same complexity, right? So that is what we call it, like another kind of complexity, which is also called the memory complexity of a strategy. Like, so how much amount of memory you need, right? So for example, when you are talking about computational complexity, you talk about time and space. Like I would need this much amount of time, this much amount of space. Here, I would also talk about whether the memory is exponential, the polynomial, or some what sort of what amount of memory is equal. Okay, good. Now, extensions like we talked about stochastic games, like there can be games which consider real time. For example, if you have timed automata, have you heard of timed automata? Like, okay, so you did a course on timed automata sometime? Yeah, right. So there can be games on timed automata also. Like you have real time, you can have games on timed automata. Then there can be these objectives which are like qualitative objectives like reachability, safety, like repeated reachability. Bushy, so are you aware of this bushy objective? Some of you know. Okay, so I think this is good that we'll have more things to talk about. So these are like a repeated reachability is like a bushy. So I just talked about just a reachability objective, right? That you have to go and reach that L3. But if you say that, oh, I would like to reach that L3 again and again, like I would like to do infinitely often, I would like to come to L3. So this is like a repeated reachability. And then there can be quantitative objectives, like there is a shortest path, then there is a like I would like to reach there, there's a shortest path kind of a thing. There are weights, maybe there are weights, and then there can be weighted reachability. And then there are other things like mean payoff, like which is like, well, there are these weights on the edges, and there is an average which I would like to get, right? I mean, very broadly speaking. Then there can be some discounted payoff. So discounted is like initially I get some payoff, and then every time as time passes, there is a discounting of the payoff that is happening. Like suppose first I get a payoff of, let's say, n, then I would get some d times n, where d is less than 1. Then there is d squared times n, d cubed times n. And this is usually used whenever you are talking about, in learning setup, people talk about reinforcement learning and things like that. What kind of objectives they want to optimize. So this is discounted payoff is one of the very common objectives that people usually like implement to find a policy. And so they are also in reinforcement learning also often you want to find a policy, but there the idea, I mean, the way you do is like you don't have an entire idea of the system, but you try to learn the system or try to give some reward, and based on which you want to find a policy. And yeah. And then there is window min payoff, which my student Prangshu works on. So if you want to, I mean, it's like a mean payoff, but you have windows and you want to make sure that there is a window which is kind of moving. And in every window, I want to ensure that I have this much of payoff. Like, for example, I say that I have invested some amount, and then I would like to ensure that every year I am getting certain amount. I want to ensure that. Okay. And there can be some probabilities associated with that and things like that. There can be multiple portfolios. I can say optimize the expectations and things like that. Right. So again, just to mention that there are certain kinds of objectives. So these are called omega regular objectives. Like, so we will see that in the next lecture itself. What does omega regular mean? At least understanding the conditions, right? So we will talk about Bushi objective to start with, and we'll talk about what is omega regular. So all of you know regular, right? Like regular languages over finite words. We'll talk about omega regular languages, because here we are going to talk about, in this course, infinite state systems or infinite games, right? So our words will also be infinite. And now from regular we will sort of, like get promoted to omega regular and things like that. And so when these are there are so we'll look at some of the games, not may not be all. So if you talk about parity games and Rabin games, like this is parity is one kind of a condition. Like I was talking about like safety condition, right? I was talking about reachability or liveness, right? So repeated reachability, like Bushy. So parity is something which is a more general objective. So we will talk about it maybe the next or the in 2 lectures from now. So parity is one such specification, like it subsumes all these reachability, safety, repeated reachability. It's a very broad class of objective, but what one can show, which we may not be able to cover in this course. I mean, it requires some maybe another reading course or something. That even for parity objective also, just it's good to know that one can show memoryless strategies. Okay. So we'll try to study at least Bushi and something called Kobushi in this course. but may not be able to. I mean, there. So I'll come to the like how the course is sort of like about the gradings and those kind of things in the last 5 minutes. So this can also be some seminar topic and things like that. And then this window mean payoff, it requires uh, finite memory strategy. Now, when you talk about, let's say, sure and almost sure parity. So what is a sure parity? Sure means that no matter how the environment behaves, so every individual execution has to satisfy the parity condition, right? So that is like a sure parity. It's sure. Irrespective of how the environment behaves across all the executions of the system, right? Like all these traces that we were generating, this I cross O omega, all the traces should uh, satisfy the parity condition. That is called a sure parity condition. And what is an almost sure parity? Does anyone, can somebody say what is an almost sure thing? I mean, when you say almost surely one should satisfy with probability 1, okay, then we would say almost surely. With not just high, with probability 1 you would like to satisfy, right? So can you think of, like, if I give you a probabilistic system, like let's say a Markov chain, is the sure the same as almost sure with probability 1? Do you think like they're the same or they're different? I mean, can you have an execution which appears with measure 0 or with probability 0?
Some probabilistic transitions where, like, suppose you are released from this state to that state and it has an objective probability.
Yes.
Then if you do it infinitely many times, then
Sure.
almost surely you will reach.
Right, right. So, for example, if I tell you, I mean, you were right. So, I'm just trying to sort of reiterate that. So, suppose you have something like this, and you have P here, right? And here you have a probability 1 minus P, right? So, this is a Markov chain. This is an example of a Markov chain. Maybe you have a self loop here. Again, this with probability 1, right? So, what is the probability of reaching S2 from S1? What is the probability of reaching S2 from S1?
Like eventually?
Eventually, yes. It's 1, right? With probability 1, you can just try to see in 1 step, 2 steps, 3 steps, 4 steps, right? Like, so you will have a GP and then you add it, series, and then you will have, right? I mean, right? The probability is 1. Eventually, you will reach S2 is 1. But can I say that I will surely reach S2? Can I say that I'll surely reach S2? No, because there is a measure 0 path. So there is a measure 0 infinite path which just keeps repeating here. It can just keep on taking the self loop, right? So that is what is called, it's an almost surely satisfying the reachability property, but not surely reaching surely reaching uh, the surely satisfying, not surely satisfying the reachability property. When we talk about surely instead of almost surely, then it's just a rule of thumb is like you can change the probabilities with some kind of an adversary, like an environment state, right? You can change the probabilistic transition by transitions from an adversary or an environment. When you talk about surely, even in a Markov chain or in a probabilistic system, right? This is a rule of thumb. Then you can say that, okay, surely now the environment you can think will always send you along this edge. Clear? So that's just. And so if you talk about combination of sure and almost sure parity, like, so for example, I want a policy which will surely satisfy. I did not talk about what the parity condition is, but you can think of this is like a more general sort of, like I have talked about Bushy, which is like repeated reachability. It's something which is even more generic, right? And if I talk about give me a single policy, which will satisfy, say, a parity P1, like a Bushy, let's say I will repeatedly reach this set of states surely, as well as almost surely repeatedly reach this set of states, something like that. If I ask you for this, a combination, give me a single policy which will satisfy both the conditions simultaneously together, then that may require infinite amount of memory for a generic game, right? I mean, maybe in some game you may not require for some instance, but for some instance, there can be such instances like a generic algorithm may require infinite amount of memory. Is it clear? Right? Good. So, yeah. And then one can also talk about non-zero sum games, like environment is not necessarily adversarial. So the environment also has its own set of objectives. Like the environment wants to do something else. It's not just your environment is trying to punish the system always, right? The environment has its own set of, like a rational environment has its own set of objectives, right? So you can try to just to find out some of these things just as a general knowledge, nothing if you're just interested. Try to go and search a bit about like what is this rimcast, acast, and things like that. Because these are nice things which people like, nice models which people do study when they are looking at actual verification. These are like benchmarks on which they try their different algorithms and things like that. You can also try to find out the contributions of these great people. And we are going to look at some of their works, like Amin Eliot, Clark, Alan Emerson, Joseph Sifakis. I mentioned some of them, Moshe Vardi. So this Vardi-Ulper construction is something that we'll definitely look at. Uh, Moshe Vardi and Pierre Ulper, Tom Hensinger, Rajiv Alu, Nikolai Moanjik, and so on. There are several people. Just to So what is the course objective? So this is important to understand. So we will learn formal modeling of system behavior, right? So it's not only just that the specifications are there, we learn how to model, like what are the good abstractions of the system, like what are the formal models on which we can run our algorithms for verification, for model checking. It's something which is very arbitrary. We cannot do much. I mean, at least theoretically, we cannot study. If you want to give complexity results, if you want to talk about lower bounds, for example, you have Turing machines, right? It's a formal model. You have Automata, it's a formal model. Markov chains, it's a formal model. So what are these such formal models, and how for a specific kind of objective or a specific kind of systems, what are the formal models? That's something we would like for example, if you are talking about timed behavior, then there is timed automata. So these are the things that we'll talk about. Then we'll talk about these logics which specify how to, I mean, which talk about how to specify a behavior in certain logics, right? So these property specifications. Then there are like this, right? So whether, for example, like if we have a counter example, I mean, then how we can analyze the counter example and try to understand how the system may require a change. Uh, and all these algorithms, and so these are the main things we'll be looking at, these mathematical concepts underpinning the algorithms, and the different techniques for verification and their complexity, right? The related complexity of these problems. And when I say verification, I also mean like as well as some and synthesis also, right? Which are like these games. And then what are the policies, how much amount of memory you required for these policies and things like that. Um, and so this is actually, I've written this in the next point, that synthesis is about how to automatically construct correct systems from specification. So this is the synthesis part, right? And again, synthesis will also have its own, uh, like what is the complexity of the memory, like the memory complexity as well as the computational complexities and things like that. And we will also try to make ourselves familiar with some of the verification tools. Like there may be some homework assignments where you may be asked to model some system using the tool and to see like how I mean the tool works, and whether the tool gets stuck if the system is too big and things like that, right? So so this is about the grading. So we will have roughly 4 to 5 assignments, and in total it will have something between 40 to 50%. And then there are there may be a couple of presentations, like these are seminars on some research paper. And so which will have one tool, like you may have to model some system in a particular tool, and then also give a brief overview of the tool, how the tool works, and then yeah. And there will be one final exam. So this is the broad idea of the course. And yeah, so this is pretty much. Do you have any question? Anybody? Any questions? So one thing I wanted to also tell you is that so this week we are going to have the lecture on Friday, as it is there in the routine, the next lecture. From next week, I don't exactly know. Monday it will be there, as we are having. We may move to Wednesday because Prahlad requested me that if we can have it on Wednesday because some of the students in his course might prefer the Friday slot. And this is one thing. The other thing, yeah, I also want to know, there are these 400 level courses. Any of you planning to take like this? So there is a 400 level course by Hari. I think, does anybody have the high dimensional geometry? And Prahlad is taking a course like quantum coding theory. Okay, so yeah, so